Hello friends, welcome to EPG Pathshala. I am Atika Tajdar, Department of Geography, Jamia Millia Islamia. Today we will discuss about image enhancement. Image enhancement means to improve the visibility of any portion or feature of the image, suppressing the information in other portion or features. Information extraction technique help to get the statistical information about any specific feature or portion of the image. Nowadays, image enhancement is applied in the field of medical imaging, analysis of satellite image, etc. The satellite image having insufficient information or details, having a lots of extra information which is unwanted. It may reduce the noise level by using the enhancement technique and eliminate by using some filtering technique. Even filtering techniques are a part of image enhancement techniques. These techniques are discussed in detail and illustrated in this module. Digital image processing, which is also called DIP, involves the modification of digital data for improving image qualities with the aid of computer. The processing helps in maximizing clarity, sharpness and details of feature of interest toward information extraction and further analysis. Image enhancement play a vital role in analysis and interpretation of remotely sensed data. Particularly data obtained from satellite, which is in digital form, can best be utilized with the help of digital image processing. Image enhancement algorithms are applied to improve the appearance of an image for human visual analysis. The principal objective of the image enhancement is to modify attribute of an image to make it more suitable for a given task and a specific observer. During this process, one or more attributes of the image are modified. This technique is widely applied in geophysical image and used to make it easier for visual interpretation and geological understanding. For example, you can remove noise, sharpen and brighten an image and improve perceptual aspects such as image quality, intelligibility or visual appearance and make it easier to identify key features. The enhancement technique changed the original digital number, which is also called DN value, permanently. Therefore, those images cannot be used for many digital analysis, example image classification. These techniques are applied either to single band image or separately to the individual band of a multi-band image set. Image reduction and magnification. Image reduction. Image reduction technique allows the analyst to obtain a regional perspective of the remotely sensed data. The computer screen cannot display the entire image on the screen unless reduce the visual representation of the image. It is commonly known as zoom out. Figure 2 shows the hypothetical example of 2x image reduction achieved by sampling every other row and column of the original data. Results show that the new image consisting of only quarter or 25% of the original data. Image magnification. Image magnification is very useful technique when the analysis is trying to obtain the detailed information about the spectral reflectance or emittance characteristic of a relatively small geographic area of interest, and it is also used to match the display scale of another image. It is commonly known as zoom out. Figure 3 shows the hypothetical example of 2x image magnification achieved by replacing every row and column in the original image. The new image will consist of 4 times as many pixels as the original scene. Row and column deletion is the simplest form of image magnification. To magnify an image by an integer factor m squared, each pixel in the original image is replaced by an m into m block of pixels, all of the original pixel values. Method of enhancement, spatial domain enhancement techniques and frequency domain enhancement technique. Let us discuss about spatial domain enhancement technique. It is modified the gray scale or intensity value of image and it is based on direct manipulation of pixel in an image. Spatial domain process are denoted by the expression g under bracket xy is equal to t under bracket f and xy, where f under bracket xy is input image, g under bracket x and y is processed image. f is the intensity value at the pixel located by x and y. T is defined the operator on f over some neighborhood region of x and y. Intensity value at the pixel located by x and y after process does not depend on the intensity value at pixel located by x and y which are there in the neighborhood of x and y alone. It is also depend on the intensity which are there in the neighborhood of the x and y point. The value of a pixel with coordinates x and y in the enhanced image is the result of performing some operation on the pixels in the neighborhood of x and y in the input image. In frequency domain method, the image is first transferred into frequency domain. It means that Fourier transform of the image is computed first. Fourier analysis is a mathematical technique and is used to separate the satellite image into the various spatial frequency component. Frequency domain filtering operation is shown in figure 4. Contrast enhancement. Remote sensing images have played an important role in many fields such as meteorology, agriculture, geology, education, etc. Contrast enhancement techniques are required for better visual perception and color reproduction. The range of brightness value present on image is referred to as contrast. Contrast enhancement techniques have been widely used in many applications of image processing where the subject quality of image is important for human interpretation. A common problem in remote sensing is that the range of reflectance value collected by a sensor may not match the capabilities of the color display monitor. In digital image processing, the contrast enhancement for satellite image in the field of remote sensing, a lot of work has been done to get better the quality of image such as histogram equalization, multi-histogram equalization and pixel dependent contrast preserving. Contrast generally refer to the difference in luminance or gray level value in an image is an important characteristic. It can be defined as the ratio of the maximum intensity to the minimum intensity over an image. Contrast ratio is equal to BV maximum upon BV minimum, where BV maximum is the maximum brightness value and BV minimum is the minimum brightness value. Let us discuss about the contrast enhancement. Linear and non-linear transformation functions such as image negatives, logarithmic transformations, power law transformation and piecewise linear transformation will be discussed. Histogram process and histograms of 4 basic gray level characteristics will be introduced. The key to understand contrast enhancement is to the concept of an image histogram. A histogram is a graphical representation of satellite data. Linear contrast enhancement. Linear contrast linearly expand the original digital value of the remotely sensed data into a new distribution. It is also referred to as a contrast stretching. These type of enhancement are best applied to remotely sensed images with Gaussian or near Gaussian histograms, meaning all the brightness value fall within a narrow range of the histogram and only one mode is apparent. There are 4 methods of linear contrast enhancement: minimum maximum linear contrast stretch, piecewise linear contrast stretch, saturation stretch, minimum maximum linear contrast stretch. In this technique, the original minimum and maximum value of the data are assigned to a newly specified set of value that utilize the full range of available brightness value of the display unit. To perform linear contrast enhancement, the analyst examine the satellite image statistics and determine the minimum and maximum brightness value in band K, maximum K and minimum K respectively. BV out is equal to BV in minus minimum K upon maximum K minus minimum K. Quant K, where BV out is the original input brightness value and quant K is the minimum value of range of brightness. Piecewise linear contrast stretch. It involves the identification of a number of linear enhancement steps that expand the brightness ranges in the modes of the histogram. The piecewise linear contrast stretch is similar to the minimum maximum linear contrast stretch, except this method uses a specified minimum and maximum value that lie in a certain percentage of pixel from the mean of the histogram. In the piecewise stretch, a series of small minimum maximum stretch are set up within a single histogram. It is very powerful enhancement technique. A piecewise linear contrast stretch normally follows two rules. First, data values are continuous, there can be no break in the value between high, middle and low range. Second one, data value specified can go only in an upward increasing direction, as shown in figure 7. In the piecewise linear contrast stretch, several breakpoints are defined that increase or decrease the contrast of the image for a given range of values. The minimum and maximum values are stretched to the value of 0 and 255 at a constant level of intensity. Saturation linear contrast stretch. The saturation contrast stretch is also referred as percentage linear contrast stretch or tail trim. It is similar to the minimum maximum linear contrast stretch, except this method uses specified minimum and maximum values that lie in a certain percentage of pixel. Sometimes these tails of the histogram is enhanced more prominently. This is the main of this method. In this method, the information content of the pixel that saturate at 0 and 255 is lost. However, the remainder part of histogram is more enhanced compared to minimum to maximum linear stretch. Non-linear contrast enhancement. Non-linear contrast enhancement often involve histogram equalization through the use of an algorithm. In the non-linear contrast enhancement technique, each value in the input image can have several values in the output image, so that objects in the original image lose their corrective relative brightness value. Usually, non-linear enhancement bring out the contrast in one range while decreasing the contrast in other ranges. There are three types of non-linear enhancement technique: histogram equalization, adaptive histogram equalization, and homomorphic filter. Histogram equalization is another non-linear contrast enhancement technique. It is one of the most useful methods for the non-linear contrast enhancement. It usually increases the global contrast of the satellite images. It creates an output version of satellite image which maximizes the contrast of the data by applying a non-linear contrast stretch that redistribute pixel values so that there are approximately the same number of pixels with each value within a range. When the histogram value of a satellite image is equalized, all pixel values of the image are redistributed. Histogram equalization can also separate pixel into distinct groups if there are few output value over a wide range. It is not necessary that contrast will always be increased in this. There may be some cases where histogram equalization can be worse. In this case, the contrast is decreased or it does not force the distribution flat, which means the number of pixels in each intensity level distributed equally. The total number of pixels is divided by the number of bins, equaling the number of pixels per bin as shown in the following equations, where n is number of bins. If there are many bins or many pixels with the same value or values, some bins may be empty. T is equal to total number of pixels in the image. A is equal to equalized number of pixels per bin. Histogram equalization example is, in this example 10 bins are rescaled to the range of 0 to 9 because the input value range from 0 to 9, so that the equalized histogram can be compared to the original. The output histogram of the equalized image is shown in figure 8b. In the output, histogram is not exactly flat, since the pixel can rarely be grounded together into bin with an equal number of pixels. There are 240 pixels represented by this histogram. To equalize this histogram to 10 bins, 240 pixels divided by 10 bins is equal to 24 pixels per bin is equal to A. Following equation is used to assign pixel to bins, where A is equal to equalized number of pixel per bin, Hi is equal to number of values with the value I, Hk is the number of pixel per bin, K is equal to a particular bin number, I and T is equal to integer factor, Bi is equal to bin number for pixel with value I. There is also one important thing to be noted here, that during histogram equalization the overall shape of the histogram changes, whereas in histogram stretching the overall shape of histogram remains same. Adaptive histogram equalization. In adaptive histogram equalization, the satellite image divided into several rectangular domains compute an equalizing histogram and modify levels. This method enhances the contrast of images by transforming the values in the intensity image. Contrast is increased at the most populated range of brightness value of the histogram. It automatically reduces the contrast in very light or dark part of the image associated with the tails of a normally distributed histogram. According to this method, we partition the given image into block of suitable size and equalize the histogram of each sub block. In order to eliminate artificial boundaries created by the process, the intensities are interpolated across the block region using bicubic interpolating function. Homomorphic filter. In the image enhancement technique, the homomorphic filter is used to remove the multiplicative noise. It is used in the log spectral domain to separate filter effect from excitation effect. Enhancement in the log spectral domain can improve sound intelligibility. For homomorphic filter to be effective, it need to be affect the low and high frequency component of the Fourier transform in different way. For homomorphic filter to be effective, it need to affect the low and high frequency component of the Fourier transform in different way. Filters. There are two types of enhancement technique called spatial domain and frequency domain technique, which are categorized again for smoothing and sharpening the images. We consider the filtering in frequency domain using FFT. Use of the term frequency domain and frequency component is reality. Use of the frequency domain and frequency component is really no different from the term time domain and time component, which we would use to express the domain and value of fx if x were a time variable attenuated to some degree. Low pass filter, which is also called smoothing. A low pass filter is a filter that passes low frequency signal and attenuates signals with frequencies higher than the cutoff frequency. The actual amount of attenuation for each frequency varies depending on a specific filter design. Smoothing is fundamentally a low pass operation in the frequency domain. There are several standard forms of low pass filters are ideal, Butterworth and Gaussian low pass filters. High pass filters, which is also called sharpening. A high pass filter is a filter that passes high frequencies well, but attenuates frequencies lower than the cutoff frequency. Sharpening is fundamentally a high pass operation in the frequency domain. There are several standard forms of high pass filters such as ideal, Butterworth and Gaussian high pass filter. All high pass filter is often represented by its relationship to the low pass filter. Indices. Band rationing of satellite image is the arithmetic operation that is most widely applied to images in the application of remote sensing such as geological, forestry and agriculture. In this enhancement technique, the DN value of one band is divided by that of any other band in the sensor array. Creating ratio images is done using the following general formula, where BVIJR is equal to output ratio values for pixel at row I and column j. BVIJK and BVIJL are the brightness value at the same location in the band K and L respectively. If BVIJK and BVIJL both values are similar, resulting proportion is a number close to 1. If numerator number is low and denominator high, the quotient approaches 0. If there is reverse, high numerator, high denominator, the number is well above 1. The ratio of their reflectance between the two bands should always be very similar. 3-band ratio images can be combined as color composites which highlight certain feature in distinctive colors. Commonly used ratios indices are as follows. Vegetation index DNNIR upon DNR, where DNNIR is equal to brightness value of pixel in NIR band and DNR is equal to brightness value of pixel in R band. Normalized difference vegetation index, also called NDVI. In NDVI, the difference between the near infrared and red or visible reflectance is divided by their sum. The NDVI has a range limited to a value from -1 to 1. Data from vegetated areas will yield positive values from the NDVI due to high near infrared and low near and low red or visible reflectance. NDVI is calculated as follows. NDVI is equal to NIR minus red upon NIR plus red. Normalized difference snow index, which is also called NDSI. Normalized difference of two band, one in the visible and one in the near infrared, a short wave infrared part of the spectrum. It is used to map snow. Value of NDSI greater than 0.4 indicate the pressure of snow, indicate the presence of snow. The NDSI was originally developed for use with Landsat TM and ETM plus band 2 and 5 or MODIS band 4 and 6. However, it will work with any multispectral sensor with a green band between 0.5 to 0.6 micrometer and an NIR band between 0.76 to 0.96 micrometer. A snow index for the Landsat thematic mapper and moderate resolution imaging spectrometer. Geoscience and Remote Sensing Symposium IGARSS 94 volume 4 Surfaced and Atmospheric Remote Sensing Normalized Difference Built Up Index, also called NDBI. This index highlights urban areas where there is typically a higher reflectance in the short wave infrared region compared to the near infrared region. Application include watershed runoff prediction and land use planning. The NDBI was originally developed for use with Landsat TM band 5 and 4. However, it will work with any multispectral sensor with a SWIR band between 1.55 to 1.75 micrometer and an NIR band between 0.76 to 0.9 micrometer. Principal component analysis. Principal component analysis, also called PCA, is one of the statistical techniques frequently used in signal processing in the data dimension reduction or to the data decorrelation. There are two distinct applications of PCA in image processing. They are image color reduction, determination of object orientation with the help of eigenvector. Quality of image segmentation implies two results of the following process of object orientation evaluation based on PCA as well. Presented paper briefly. Principal component analysis is a technique in which the original remotely sensed data set is transformed into new data set which may better capture the essential information. This transform is known as principal component transformation, also called PCT, or principal component analysis, which is PCA. Principal component analysis belong to linear transform based on the statistical technique. This method provides a powerful tool for data analysis and pattern recognition, which is often used to signal and image processing as a technique for data compression, data dimension reduction, or their decorrelation as well. There are various algorithms based on multivariate analysis or neural network that can perform PCA on a given data set. The objective of this transform is to reduce the number of bands in the data and compress as much of the information in the original band into fewer bands. The new band that result from this statistical procedure are called principle. The PCA theory principal component analysis in signal processing can be described as a transform of a given set of n input vectors or variable with the same length k formed in n dimensional vector, where x is equal to x1, x2 with x in numbers t into a vector y according to 1. Y is equal to a under bracket x minus mx. Mx is equal to E under bracket x is equal to 1 upon k. Matrix A in equation 1 is determined by the covariance matrix Cx. Rows in the A matrix are formed from the eigenvectors of Cx ordered according to corresponding eigenvalues in descending order. The evaluation of the Cx matrix is possible according to relation. Cx is equal to E x minus mx, x minus mx t is equal to 1 upon k minus k x t k minus mx mx t. As the vector of input variable is n dimensional, it is obvious that the size of Cx is n into n. The elements Cx I lying in its main diagonal are the variance. Cx I is equal to xi mi into 2. Value Cx ij determine the covariance between input variable xi xj. Cx ij is equal to E xi minus mi into xj minus mj. The rows of A in equation 1 are orthonormal, so the inversion of PCA is possible according to relation. X is equal to ATY plus mx. PCA uses for image compression, data volume reduction is a common task in image processing. There is a huge amount of algorithm based on various principles leading to the image compression. Algorithm based on the image color reduction are mostly less, but the results are still acceptable for some applications. The image transformation from color to the gray level intensity image belong to the most common algorithm. Its implementation is usually based on the weighted sum of 3 color component RGB according to relation. I is equal to W1R plus W2G plus W3B. The R, G and B, also called red, green and blue band matrices, contain image color components. The weights Wi were determined with regarding to the possibilities of human perception. The PCA method provides an alternative way to this method. The idea is based on equation 6, where the matrix A is replaced by matrix AI, in which only I is largest instead of n. Eigenvalues are used for its forming. The vector x of reconstructed variable is then given by relation. X is equal to AKT plus mx. PCA used for determination of object rotation properties of PCA can be used for determination of selected object orientation or its rotation. Edge detection must be used at first. Binary image containing object boundary or its area in black or white pixel on the inverse background result from this process. After that, two vector A and B containing the Cartesian coordinates of object's pixel can be simply formed. The vector x in the equation 1 is in this case a two-dimensional vector consisting of A and B respectively. The mean vector mx and the covariance matrix Cx are computed as well as its eigenvector. Its two element vectors E1 and E2 enable the evaluation of object rotation in the Cartesian axis or object rotation around the center given by mx illustrates the PCA used for determination of selected object orientation. The object boundary was detected at first by means of log filter in the original gray level image. The original has been rotated by the given angle with the bilinear interpolation method used, and the process of image segmentation and PCA has been applied again. Resulted eigenvector E1 and E2 are drawn in each binary image 2 and their orientation were compared with the rotation angle. Review of PCA in satellite image analysis. To perform the principal component analysis, apply a transformation to a correlated set of multispectral satellite images. This technique is widely used in digital processing of multispectral image. PCA and image fusion technique both are often used to enhance an image, particularly in the land use and land cover classification of satellite image, and it is used for improve the accuracy of classification. In the field of remote sensing, PCA may also be useful for reducing the dimensionality of hyperspectral data set without much loss of data information. There are certain vectors called characteristics vector or eigenvector that gives the direction of the new axis. This is a general method of determining the axis of the new coordinate system. Thank you.